You will need to understand the periodic trends in terms of atomic size. Shown here is the periodic table with respect to the um, size of atoms as you go down a group or a column of the periodic table. Atoms tend to get bigger because we have more and more shells. And this is generally true no matter which of the groups you're talking about. This can be contrasted with what happens when you go across a period. It turns out that if you go from right to left within a period, the atoms tend to get bigger. And so, in fact, the very largest of the atoms is in the lower left-hand corner of the periodic table, whereas the smallest atoms tend to be in the upper right-hand corner. This generally corresponds with the metallic versus non-metallic character. So generally metals tend to be bigger than the non-metals. There are, as I mentioned just a moment ago, there are two general factors that affect the size of the atom. The first is what is the principal quantum number for the valence shell? If you increase the principal quantum number for the valence shell, that shell is further and further away from the nucleus, and hence the atomic radius of that atom increases. This is what happens when you go down a group on the periodic table. In contrast, what happens when you go and add more and more protons in the nucleus, you have a situation that is more and more positive charge. You would expect that the negatively charged electrons should be more and more attracted to that, but it's the valence electrons that primarily define the size of the atom, and the electrons that are in between the valence electrons and the nucleus are the so-called core electrons. And so what we really need to do is consider the overall core charge, or the so-called effective nuclear charge, and this is what determines how effectively the valence electrons are attracted to the nucleus. On this slide, I would like to try to describe the effective nuclear charge for a particular atom. So we're going to start out with an atom way on the left-hand side of the periodic table, for example, sodium. Sodium is atomic number 11. There are 11 protons in the nucleus, and so its nuclear charge is 11 plus. It turns out that there are 10 electrons that are in the inner shells, and so the valence electron, the 11th electron, is in the outer shell. As far as the valence electron is concerned, the inner core electrons are essentially blocking the valence electron from feeling all of the positive charge from the nucleus. So in essence, the core charge of this particular atom is a sum of the 11 positives and 10 negatives from the core electrons. So it has an effective nuclear charge of +1. It turns out that all of the elements in the first group, all of the alkali metals, have exactly the same amount of core charge. Now, if you go to an atom that is way over on the right-hand side of the same period as sodium, in this case, chlorine has 17 protons in the nucleus. Now, what we have essentially done here is we've added 6 more protons to the nucleus and an additional 6 electrons in the valence shell. But for any one individual valence electron, the valence electrons do not feel any more shielded because of the additional valence electrons, and because there's not any more core electrons. And so, in essence, each of the valence electrons begins to feel more and more positive charge, and so the chlorine atom indeed ends up being much smaller because of that than the sodium atom. So we say that the effective nuclear charge of the chlorine atom is higher than the effective nuclear charge of the sodium atom. So if we wanted to calculate the effective nuclear charge for chlorine, it would be 17 protons minus the 10 electrons that are in the core, and so the effective nuclear charge for chlorine is 7 plus, as opposed to the sodium, which was only 1 plus. So here we have the formula for calculating the effective nuclear charge. It's approximately the number of protons in the nucleus minus any of the core electrons. Shown here is a plot of atomic number versus atomic radius. What you see here is a regular repeating pattern every time one goes from left to right on the periodic table. You see a spike in the atomic radius when you get to an element in the first column of the periodic table. So one of the things that you can see fairly readily is that as you go down the elements in the first group, the atoms get larger. So when we go from hydrogen to lithium, sodium, potassium, rubidium, cesium, there's a general increase in the size due to the increase in the N value for the valence shell. The valence shell is farther and farther from the nucleus. If we go from left to right within a period, if we start with, say, potassium, the atoms generally get smaller. There's at least one glitch in that, and that occurs right in the middle of the transition metals. That's where you end up having a half-filled shell. There are several other glitches in this plot, but these are things that are beyond the scope of what we need to discuss for this class.